Singularity.
My name is Nicola, and you're watching Singularity FM, the place where we interview the future. If you guys enjoy this podcast, you can show your support by either writing a review on iTunes or by simply becoming a patron via patreon.com/SingularityFM. Today, my guest on the show is none other but Professor Stuart Russell. Professor Russell is a professor of computer science at UC Berkeley, as well as the co-author of the most popular textbook on artificial intelligence, titled Artificial Intelligence: A Modern Approach. Welcome to Singularity FM, Stuart.
Thank you, Nicole.
Fantastic. So, if I were to ask you to introduce yourself in your own couple of words, how would you introduce yourself? Who is Stuart Russell?
Well, I think it depends on who I'm talking to, but for this audience, I'm a professor of computer science at Berkeley. I've been at Berkeley for 32 years, and before that, I first began doing AI when I was about 14. Very soon after I learned what a computer was. So I think my first computer was actually a programmable Sinclair calculator. And you could write programs with, I believe, 21 steps altogether. And soon after that, I started doing a computing science A-level while I was in high school. And my first significant program was a program that learned to play tic-tac-toe by itself, so a kind of reinforcement learning program. Wow. And then I wrote a chess program and so on. So this was all more than 40 years ago. And at that time, it didn't seem there was any plausible route to doing AI as an academic career. It wasn't considered a real subject. So I was a physicist, but when I finished my undergraduate degree in physics, I switched to computer science. I did my PhD at Stanford, and then I moved to Berkeley from there.
Wow, that's fascinating. I was going to ask you what was your first love, whether that was physics or computer science. But it seems that physics was kind of like a temporary detour away from computer science, which was kind of the more practical approach in life. And then you eventually returned back to your first love. Is that a true interpretation?
I don't think it quite worked that way. I mean, I growing up, I wanted to be a scientist, a particle physicist, to discover the next thing beyond quarks or the next grand unified theory. But when I was finishing my physics undergraduate degree, I had applied to physics PhD programs, and I went to talk to some leading physicists. I talked to Chris Llewellyn-Smith, who was on his way to becoming director of CERN, so one of the leading particle physicists in the world. And the picture that he laid out for what was happening in particle physics, to me, was sort of anti-inspiring. And when I spoke to the grad students and postdocs in physics, they expressed something similar, that in fact it was incredibly difficult to make significant contributions, that if you were lucky, you would be 257th author on some paper about a particle accelerator experiment, and you'd gradually work your way up the list of authors, and you tried to do that fast enough so that you could get a faculty position before your time as a postdoc ran out, and then you'd become a taxi driver. So it didn't seem like theoretical particle physics was maybe the field with the brightest future, whereas AI was really at the beginning. I mean, it was sort of 1905 or even 1895 in AI. Mm-hmm. Where all the big major discoveries are still to be made.
Mm-hmm. Yeah. And then, so if we roll the tape even further than when you were younger than 14 years old, was there something before that pushed you into this sort of computer science or physics path? And maybe, and I'm just like fishing here, but I watched an interview with you where you said that you read a lot of philosophy at some point in your life. So I'm wondering if that was before or after that.
So the philosophy I read partly because my girlfriend at Oxford was in the philosophy program, And also my PhD thesis was about the use of knowledge in machine learning, and that actually leads into a lot of the philosophy of science literature. So I actually learned a lot about philosophy during my PhD. But no, I think the interest in computer science was really sparked by my programmable calculator, and then doing a computing science A level. But the interest in AI also came from a book that I won as a prize. So I won a math prize at school, and I got to choose a book for that prize. And the book I chose was called The Thinking Computer by Bert Raphael, who was one of the first co-editors of the AI Journal. And that was actually, it's a very good book for a layperson to learn, at least in 1975 or whenever, to learn about AI and the various exciting ideas that went into it. So those multiple influences. And then another thing that happened was just from the evolution of my own thinking about good and bad decision making and so on. I kind of developed this idea, which I discussed at length with my dad, who also had a background in philosophy, that effectively everything about life could be reduced to a single number, which I didn't know was called utility, but and that you could make all decisions by maximizing the expected value of this numerical degree of desirability of some future sequence of events. And so that idea that there was a clearly definable, justifiable basis for decision making was something that I had started thinking about from the age of 11 or so.
Is that a fact or is that a hypothesis? Because I think there's still a debate about whether we can reduce everything down to a single number, isn't there?
It depends who you ask.
Okay.
So some people would say there's no debate about whether you can. There's a debate about whether people do.
Yes.
So are people actually conforming to the prescriptions of rationality and so on? But I think the fact is that the way the axioms work to derive the basis for the existence of utility functions it simply follows from the fact that we have to make choices. And sometimes you have to make a choice between going to work and, watching the sunrise and reading poetry. You have to make a choice. Mm-hmm. So you might say, well, how can you reduce poetry and sunrises to a single number? And you don't if you never have to make a choice. But you do have to make choices, and sometimes the world forces these choices on you. And so whenever you make a choice, you are in effect creating a ranking. And when you take rankings plus uncertainty, you get a numerical scale. And there's no escaping from that conclusion as far as I can see.
So is it fair to say that then, and I don't even want, I still want to stay in the personal realm a little more, but is it fair to say that in a way, since you were 11 years old, then you're kind of basically translating this kind of decision-making system or philosophy, if you will, if you want to call it, or framework rather, into the realm of the machines by creating AI, which is trained within and follows such a system, perhaps?
Yeah, I think once you have that realization, you automatically, well, at least I automatically think, okay, if it can be defined in this way, then it could be encoded. It can be turned into a procedure. It can be made into a program, and a machine could, in principle, be making decisions using the same approach. And so to me, that was very exciting. And in the end, that view became the textbook sometime later. So the textbook was 1994. So I guess about 20 years later, it became the textbook.
Mm-hmm. Well, let me ask you about the textbook then, because I watched an interview where you said that the textbook became unreasonably successful very quickly. Can you unpack that for us a little bit? What do you mean by, especially the word unreasonable here is what's kind of surprising me.
I just think we weren't really expecting it. There were a number of other textbooks. There was Pat Winston's textbook. There was Drew McDermott's textbook. There was Rich and Knight, Elaine Rich, and Kevin Knight's textbook, all of which are interesting and have, and I guess also Luger and Stubblefield. So they had roughly equal market shares, I guess. I don't exactly know, but so we were expecting to join this group of textbooks, and we thought we had some advantages. We partly being more recent, so we had more up-to-date stuff, particularly on probability, which was undergoing very rapid development, starting with Udo Pearl's book. But it turned out, I think, that the thing people liked the most was this unified approach that what we're doing is building intelligent agents, and all the different parts, reasoning, learning, decision-making, planning, they're all constituent factors in creating intelligent agents. And so I think students like that. And if students like it, then professors like teaching it. So it seemed that very quickly, maybe within just 3 or 4 years, we had become the dominant textbook in the market.
So are you saying that your kind of advantage, or what made you stand out, was kind of the unified narrative, perhaps, if I may put it this way, that you were able to organize in opposition or in contrast to the alternative textbooks?
Yeah, I think AI up until then was mainly taught as a set of different fields. There was natural language processing, which was about language. There was computer vision. There was search. There was planning. These are all just separate disciplines. If you're lucky, there was a bit of probability. But the way I think about it is, really, we're building intelligent agents. Intelligent agents is about acting in a way that is expected to achieve objectives. And the differences among the subfields actually have to do with just different specific assumptions about the environment and the objective. So is the environment deterministic? Okay, well, then you're in planning and search. Is it stochastic? Oh, well, then you're in MDPs and reinforcement learning. But the overall thing is the same. And I think making that point about AI, that it's really a unified discipline, which is fractionated not by the fact that it consists of 10 different communities, but by the fact that environments themselves come in different shapes and sizes and flavors, and different techniques are appropriate for different flavors of environment. It was both, I think, conceptually more coherent, but it was also much more generative of new research work, because once you kind of understand that, and you can say, oh, well, there isn't any work on continuous partially observable environments. Okay, why don't we work on those? Because there are lots of real examples of those, and they just hadn't been properly investigated. I would say it would be probably more healthy for the field if there were more textbooks competing, and then that. And I think one other good book that came along is the one by David Poole and Alan Mackworth and Randy Goebel.
What's the title of that one, by any chance?
I think it's called Computational Intelligence, if if I remember correctly.
Yeah, I think it sounds familiar. I haven't read it, but I think maybe.
And yeah, so that's a good book, and it has, it's a similar overall approach. It has probably a bit more concentration on logical reasoning because of the background of the authors, but it's.
Let me throw in a sidekick question, if I may, just sort of to scramble things up a little bit. Are you a dog person or a cat person?
Well, I was a cat person growing up. We always had cats, and I never particularly liked dogs. They made a lot of noise, and they tried to bite you, and so on. And then one day, so my sister, soon after I joined the faculty at Berkeley, my sister was living with me for a while, and one day she brought home a dog, and that dog became part of the family. And then later on, after I got married, we met a dog on the beach who was about to be put down.
Wow.
So he was sort of having a last weekend at the beach with the SPCA people before he was put down because they couldn't find a family, and he adopted us. So he became our family's dog, Sammy. So we've become a dog family.
Wow, good for you. Thank you for doing that. That's amazing. Okay. Wow. So you started as a cat person, you ended up being a dog person. That's hilarious. That's fantastic. What's your biggest dream? What is it that sort of makes you get up and go running sometimes towards doing your work, hopefully? Or if that does that happen even, like it excites you, like you want to rush to do it?
My dream in my academic life is that AI will contribute to a future golden age of humanity. And the more I learn about history, even up to the present day, and I understand Steven Pinker's view that things are getting better, and I largely agree with that. But the history of the human race is a great deal of misery inflicted on people for reasons I think that ultimately come down to a competition for access to sort of the wherewithal of life. Compounded with a good dose of ignorance and bigotry and tribalism and a few other things. And there's a chance that we could get past all that. What we're going to do if we do have that freedom to choose how society goes instead of things being chosen for us by the outcome of conflicts, which is the way it has been. I don't know. I'm not sure we have quite enough wisdom yet to make good choices about the future, but at least I think it will be nice for the human race to have a choice about its future.
By the way, that history of tribalism and violence that you're describing is not true only within our species, but particularly also of our species towards other species. So, for example, every year on our planet, we kill something like 73 billion animals, just like your dog was about to be put down by the SPCA. 73 billion animals annually get killed for a variety of reasons, from food to even sports and fun, if you will, or sometimes simply because they're at the wrong place at the wrong time. And that's just the animals, but we also have 1.3 trillion fish annually. So it's not only within our species that this has been going on, and it's particularly important, I think, to stress that we're doing this to the other species too. So while Steven Pinker may be correct that we have been improving our condition, he doesn't actually spend a lot of time, if any, noticing the fact that we are in the midst of the sixth extinction, and many of the other species are either threatened or already have gone extinct. And we are causing growing amount of violence and destructions to the other species.
Yep. So we could talk about that point later because it's one of the questions raised about whether AI systems should be responsive to human preferences. So some people argue that they should be responsive not just to human preferences, but also to animal preferences.
Yeah, actually, I'm bringing this, and I'm going to bring it later because, and that's one reason that we need to talk about it, but there's also other reasons that I would bring later. So, if you are sort of dreaming to bring AI that would hopefully help us solve those problems and those challenges, or at the very least alleviate them, aren't you afraid that other people are saying that maybe through your work, you're actually going to accomplish quite the opposite? You're going to bring the destruction of the human race, and they're saying that our species will be superseded, eventually replaced by the artificial intelligence. And so, in other words, instead of helping us, your work would be instrumental in destroying us. At least so the argument goes by those people.
Yeah, so I think that's about right. Except that I don't think you should think about this as a question of sort of weather forecasting. That AI is going to do this or AI is going to do that. We get to choose what kind of AI we build. So I think of it more as a steering problem. And if there's a future which is catastrophic for the human race, we should steer away from it. Mm-hmm. And roughly speaking, there's only sort of two ways to do that. One is to just stop and go the other way, right? So put an end to AI research, which I think is probably impossible. As a practical matter, AI research proceeds by people writing stuff on whiteboards. And it's very hard to pass legislation banning certain equations being written on whiteboards when you don't even know what those equations are yet. That's not ever going to work. And the other reason, of course, is that there's huge commercial interest, and as well as military and government interest. But the majority of funding right now going into AI research is happening in corporations, and so I think to just say, okay, we'll just put the brakes on and stop doing AI research is probably not feasible. Probably too late for that to happen.
I think
now.
Philip K. Dick once noted that just because something bears the appearance of being inevitable, that doesn't mean that one should go along with it willingly.
No, but it means you should try to push things in the right direction. And if you're going to put your effort into it, it should be in pushing it in the right direction, not in just standing in front of it and getting flattened. So the response that I've adopted, and this is a question that we raised in the first edition of the textbook. Back in '94, there's a section called "What if we do succeed?" And even then, it was clear that the AI community had put next to zero effort into thinking about its destination and thinking about the consequences of success. And that's primarily because the problems are extremely difficult, and making an inch of progress is incredibly painful. So maybe it was too early to be stressing this question, but I think in recent years, more and more people have been asking the same question: what if we succeed? And the concrete question is, okay, what exactly is bad about better AI? Right? You could ask similar questions like, well, what's bad about faster computers? What's bad about better medicine?
What does success look like to you is what I want to ask.
Right. Well, success would, in crude terms, would be machines that are more capable than humans across a wide range of cognitive activities.
Is that sufficient?
Is that sufficient to cause problems?
Or to help us or hurt us?
I think Yes, I think that because machines have other characteristics such as scalability and the fact that you can speed them up, so that if you had something that was in the ballpark of human capability, you could probably fairly quickly go beyond human capabilities, and you could also make millions of copies. And they can also, unlike humans who can only communicate through words, pretty much, machines can communicate at a much higher rate, so they could collaborate much more effectively with each other. And
My
go
question was,
ahead.
why are we thinking that's a good thing, right? Because here's what I'm struggling with here, and I totally get that idea. They're better at us at communication, they're better at us at cognitive capacity, at intelligence, which is to say problem solving, and we're facing major problems in our world right now, right? But let's look at, for example, Albert Einstein. He was dismayed that his German colleagues in Berlin, and Berlin was sort of the center of the scientific world at the time, basically overnight switched their attention from their scientific work and became German nationalists and started producing weapons of mass destruction, such as, for example, mustard gas and chemical weapons, and so on and so on. So those were people with very high cognitive capabilities. They were very good at communicating, at organizing, at system thinking, and yet they were putting, arguably, in my view, all those skills towards a bad end, not towards a good end. And eventually,
Right. Okay. But I mean, um, let's separate two things, right? The technical capability of the system, and then how we choose to use it. So the first question is, will we succeed in creating machines with this level of capabilities, right? So if a machine is too stupid, it's not going to have much benefit, and it's not going to have much negative impact either, because it's just unable to affect the world in any complicated way. So the question is, what's wrong with better AI? And in order to stave off this takeover of the world by machines, we need to understand exactly where the problem comes from. Right? It's not just from better AI. It seems, as far as I can tell, it's from better AI with the wrong objectives. And this is a point made by Norbert Wiener, for example, in a paper in 1960. He said, we have to be absolutely sure that the purpose we put into the machine is the purpose which we really desire.
debugging.
Well, it's not so much the debugging of the software, it's the debugging of our specification, our ability to specify the objective correctly. And that's fine when you have a stupid machine. And if it's clear that you gave it the wrong objective, you can sort of press the reset button and fix the objective and start again. And you can iterate that multiple times. But if you have a really intelligent machine, you have at least two problems, right? One is that the machine, given this objective, will actually take steps to prevent itself from being switched off, because being switched off is a guarantee that it will fail in its objective, and doesn't want to fail its objective, so it will find ways to prevent itself from being switched off. And the other thing is, of course, that it may not be clear that you've given it the wrong objective until it's way too late. And in fact, there are arguments which I think seem reasonable, that a machine that suspected that you might try to switch it off would in fact disguise its true nature, the fact that it has an objective that you may not like. It may disguise that fact until it's in an impregnable position. And so, so the question then is, what do you do about that? And my view is you have to change the way you think about AI. And not just AI, right? This is not just an AI way of thinking that machines optimize objectives. This is This is how statisticians think about it. You minimize a expected loss function. This is how control theory people think about it. You minimize a cost function, and operations research people maximize the sum of rewards. So it's ubiquitous. You could say this is the technology of the 20th century, is machinery for optimizing objectives. Mm-hmm. And I think it's the wrong definition.
Okay, perfect. Because I want to roll back the tape. I think we jumped in a little bit quickly or forward. So let me just roll back a little bit. And since you are the father of the most popular book, or at least the co-author of the most popular textbook on AI, and I have done 230 interviews on the topic, and one thing that I have noticed is that everyone has a little bit, and sometimes even a lot, different definition of what is artificial intelligence.
Mm-hmm.
So can you perhaps start by telling us what, in your view, is the proper definition of AI?
Well, I can tell you what has been the proper definition of AI for a while, which is machines that act intelligently, which means machines that act in a way that can be expected to achieve objectives. And that's been the definition. And I think it's been very helpful in moving the field forward. Particularly compared to machines that behave like humans, or machines that pass a Turing test, or anything like that, because that kind of definition is sort of non-constructive. In other words, I can't take the definition and a system design and show that the system design meets the definition. All I can do is an experiment to see if it behaves like a human, right? Mm-hmm. Whereas if I have a definition that I can reduce to sort of mathematical terms, then I can take a system design and say, I can prove mathematically, yeah, this system design satisfies this definition. And what that means, I can take the definition and work back to system designs that necessarily satisfy it. So in that sense, I think it's been very helpful. The one weak point is this notion of objectives. And we've always assumed that, the human will put that in. In the early days of AI, it was logic-based, and the system was supposed to achieve a goal. So all the planning systems, all of the search-based and problem-solving systems, the goal was the thing that the human said you were supposed to achieve. Mm-hmm. And the point is that's a mistake, because it only works as long as the human can express the goal perfectly. And the difficulty is that that's just not feasible in practice. And you get these counterexamples. You say, I want to cure cancer as quickly as possible, and then the machine will probably induce cancer in everybody on Earth. So you've got 7.4 billion experimental animals. You can try out lots of treatment combinations on all of those experimental animals who happen to be human, and we don't necessarily want them to die of cancer. So
I think you usually call this the King Midas problem. Tim O'Reilly, whom I interviewed just a couple of weeks before you, calls that actually the debugging problem, because he says that most debugging is what the programmer told the machine to do, and what the programmer later discovered that the machine understood it was told to do. And those were very often two different things, of course. Or it's recently been called the value alignment problem.
Yeah. I mean, debugging is that's a word that already has a meaning. And it has to do with errors in the code. And here we're really thinking that the code is the thing that optimizes, and then the objective is the thing that you put in once you've written all the code, and then off it goes. So it is a kind of debugging, but it's a very different kind of debugging.
Your definition is very different than Tim O'Reilly in that sense. But also, let me go back to the AI definition, because I think you're pushing away, which is very interesting, from the sort of Alan Turing, and maybe even the McCarthy classic definition of AI, which had a lot more relationship to human intelligence, didn't it?
Well, Alan Turing, actually, I don't think Alan Turing was defining intelligence that way. And I think this is the beginning of a long series of misunderstandings, which actually didn't have much impact on the AI community. Because in AI, basically nobody has ever worked on the Turing test to a first approximation. I do not know a single serious AI researcher who has even spent a day working on passing the Turing test. I think
Kevin
what the two...
Didn't Kevin Warwick work on that?
I think I rest my case. So...
okay.
So
all right.
That was a cheap shot. I apologize for that. I didn't actually know that Kevin had worked on it, but not actually. I don't know Kevin. So none of the AI researchers that I know, the people I see at conferences, year after year after year after year, nobody. There's no papers at NIPS on passing the Turing test. There's no papers at AAAI or IJCAI on passing the Turing test. These are the main AI conferences. And
Kevin Warwick claimed that a couple of years ago that there was this AI that was developed with sort of guidance from him that passed the Turing test, supposedly. And it was actually very designed to kind of win because it was pretending to be a 14-year-old boy from the Ukraine speaking.
Yeah. I saw that. So, but, again, it doesn't embody any serious AI research, and it's not the subject of papers at any of the mainstream AI conferences. I agree. So, I think the Turing test was there to ward off a particular philosophical attack on the AI enterprise, and this argument about, whether or not machines really think. And if you claim to prove on a philosophical basis that machines aren't thinking, then surely the whole effort is a waste of time. And what Turing is saying is, that's beside the point. Even if you could, it still wouldn't have any effect on the field, because what we're trying to do is create intelligent behavior. He offers the Turing test simply as an example of how you might operationalize the notion of intelligent behavior as opposed to some other kind of behavior. But he's not saying, okay, and what we need to do now is work on passing the Turing test, right? So if you look, it doesn't actually really have much in the way of research recommendations in that paper, but one of them is that we would, he talks about the child program, which is a recommendation that we use machine learning to create intelligent systems. And if you look at how he proposes to teach the child program, it's not by any means aiming to pass the Turing test. It's just aiming to become more knowledgeable and more capable of understanding the real world.
Well,
so I don't think he was really advocating the Turing test. And I think this is a mistake that the media have perpetuated over and over again, and the AI community has largely ignored it. As it should.
My notion was more connected to the fact that intelligence is something that we so far has presumed to be only almost exclusively pretty much in the human domain. And so, for example, John McCarthy in 1956, when he was defining AI, I'm reading here, says that, and also according to the Merriam-Webster's dictionary quoting John McCarthy, is that the definition has two meanings. Number one is the capability of a machine to imitate intelligent human behavior. And number two is a branch of computer science dealing with the simulation of intelligent behavior in computers. So both of those definitions, the John McCarthy sort of stream of definition, if you will, are very much connected to taking the human intelligence and bringing it or simulating it or translating it into the machine realm in a way. So it's very much kind of originating still in humanity, whereas yours is kind of fundamentally different, if I may say so.
Yeah, I think it probably is, and I think my sense is that the the two, in fact, it wouldn't particularly matter which one you pursued for the time being, because um, both goals are a very, very long way away from the current state of the art, and the two vectors point in roughly the same direction. But in the long run, if you want to make a claim that what you're doing, from a scientific point of view, is reproducing human behavior and human mental faculties, then that's a something that can only be borne out by psychological experiments, right?
Mhm.
You have to be arguing that you're actually not only doing things in the same with the same external characteristics as humans, but also by the same methods as humans. And that's cognitive science. And I think in 1956, cognitive science didn't really exist. In fact, there wasn't a clear distinction. But I think pretty soon after that, cognitive science, which is based on empirical claims about psychology, and AI kind of separated. And it's interesting talking to Alan Newell, for example. Um, so he would build this SOAR architecture, which most AI researchers, I would say, think of as a kind of if you like, almost a programming language for building intelligent systems. And Alan Newell pushed back extremely hard against that view. Right? For him, it was a cognitive model of humans. And I think for most AI researchers, they would say, well, you might think that, but we don't see it that way and we don't care. Right? What we care about is the fact that you can make it do really intelligent things by appropriate provision of knowledge and sub-goal structures and so on and so forth, the things that you have
I
to do to
I
program
think
SOAR.
Edgar
And they couldn't care
Dijkstra,
less about the fact that it was human, or
yeah,
supposedly human.
yeah, I think Edgar Dijkstra said it best when he said the question of whether a computer could think is the same as asking a question of whether a submarine could swim.
Yeah, so he was referring, I think, to the same question that Turing was addressing, and it's another way of answering that question. But you have to remember, Turing was writing in 1950, when there was a very different intellectual environment than there is today, and I think there was a very significant part of the intellectual establishment that simply did not want to countenance the possibility of intelligent computers at all.
Yeah. It's about the same time that Jane Goodall went into the forest to study chimpanzees, and she was told that, intelligence and empathy and all those things were exclusively human, that she was not to give them any names but numbers, because it was unscientific to give chimps names. They were supposed to have numbers, and that it was impossible for chimps to use or create tools. So, but
Mm-hmm.
let's go back to our conversation here. So, we talked about the definition of AI and your version of it, and you're kind of the authority because you wrote the most popular textbook or the most influential one. What about the difference that nowadays we hear a lot of these terms, such as machine learning and deep learning? How are they different from AI, and how are they different from each other? What does machine learning stand for, and how is it different from deep learning?
Okay, so machine learning is the branch of AI that studies how machines can improve their performance through experience. Um, and deep learning is one subfield of machine learning. So deep learning uses a particular hypothesis class of neural networks, typically convolutional networks with a large number of layers. So and it's been particularly successful at tasks like vision and speech recognition. But I think it's often the case that, again, partly through the media, that people think of machine learning as a replacement for AI or competitor to AI, or somehow AI is the old thing and machine learning is the new thing. I mean, machine learning has been around, as I said, since at least Turing's paper in 1950. That was his recommendation about how we should do AI, was to do machine learning. So it's absolutely been part of the field since the beginning. I mean, the term, I'm not sure when the term exactly originated, but the first machine learning workshops were started by AI researchers, people like Ryszard Michalski, Tom Mitchell, Jaime Carbonell, wrote a series of compendiums or edited a series of books called Machine Learning, which collected papers together. And that was the genesis of machine learning as a field. There was, of course, research before that. I mean, there was the early neural network research in the late 50s, 1960s, the perceptron era. There was early work on decision tree learning. And then I think when it started to be called machine learning was when people started thinking about, okay, if AI systems are going to be knowledge-based systems, how do we learn the knowledge, right? Instead of having humans specify the knowledge, it's going to be better if we can learn that knowledge from data instead.
Okay, so we just spent a little bit of time, or a lot of time, on the definitions and their origins and so on. Let us talk a little bit perhaps about what you call to be the control problem, and perhaps the three laws of Russell that you have as a solution to the control problem.
Sure. Okay, so the control problem is pretty simple. Sometimes I call it the gorilla problem, because roughly speaking, you say, okay, you make a more intelligent species than you are. How's that going to end? Well, for the gorillas, their ancestors made us, and it didn't end very well for them. So how do we avoid being in the same situation as the gorillas are with respect to us? And another way of putting it is, that intelligence really means power to shape the world in a way that satisfies your objectives. And you make something that's more intelligent than you, that it's more powerful than you. And how do you retain power over something that's more powerful than you forever? Doesn't feel all that promising. So, but that's, I think, we're going to face this, because I can't say exactly when, but I think progress in AI is going to continue. And there are remaining unsolved breakthroughs that have to happen, but they probably are going to happen. And we're going to have systems that can actually outplan us in the real world, outthink us. And that could be an issue, particularly if, for example, they have the ability to affect the world on a global scale. And arguably, when you think about the effect that, for example, Hitler had simply by speaking and writing, right? Machines can do that. Machines can connect to 5-6 billion screens, and they can have an effect on a global scale just by speaking and writing, let alone marshalling vast armies of automated physical equipment and weapons. So we need to think about this problem now, before the fact, before we create human level or superhuman intelligent systems. And
another way of putting the same question is perhaps the question that I mentioned before with the other species, which is we all originated from the same roots. Chimpanzees are our closest cousins. Genetically speaking, we share 99% of our genes with them, and yet that doesn't stop us from destroying their habitat and killing them to the point where they used to be millions and now they're in the mere thousands. So why should we be different than chimpanzees when the AIs come to be?
Yeah, so this is and I think it's a slightly different problem because we are the ones who are designing. I don't think it's right to say that the gorillas or the chimpanzees designed us. They kind of produce us by accident. And I'd say that's a good argument against doing AI purely with genetic programming, because then we really will create our successors by accident without even understanding how they work. I think that's probably a mistake. So in order to think about the control problem, we've got to think about, where do we lose control? And if we lose control when the machine is pursuing a different objective than the one we would wish them to pursue. And if they're more intelligent than us, then generally speaking, they get their objective and we don't get our objective. And if the two objectives are too different, then the outcome could be catastrophic. So we might at some point find that the atmosphere has disappeared, or that our entire food supply has been mutated beyond usability, or who knows what other kind of consequence there might be. So the problem comes, I think, from this traditional notion of AI as optimizing machinery into which we feed objectives. And so just as we believe these days that using machine learning to acquire knowledge is a bit more robust, less fragile than having to specify all the knowledge by hand, the same is probably going to be true for objectives, that to actually specify completely and correctly the human objective, and we can get into what that means in more detail, but let's assume that there's sort of humanity and there's machine, and humanity has something that it wants. How do we specify that completely and correctly by hand? I think that's probably an infeasible problem. So instead, we want it to be the case that the machine is responsible for learning about what it is that we want, as well as learning how to actually achieve what it is that we want. And so that's the basis of these three principles, which I just actually developed for the purpose of giving presentations about this. Makes it easy for people to understand, to grasp these three principles. So the first one is that the machine's only objective is realization of human preferences. And that's actually quite an important thing in itself. It means the machine has no objective of its own. So I'm, in some sense, contradicting Asimov's third law, which says the machine is supposed to preserve its own existence. There is no reason to have that law, because in order to achieve human preferences, generally speaking, the machine is going to want to preserve its own existence simply to continue being helpful to humans. And there's no other reason to do it, right? If you give the machine another reason to do it, then you're actually creating a conflict between human preferences and the machine's desire for self-preservation, and that conflict should not exist. The second principle is that the machine is going to be uncertain about what human preferences are. And this turns out to be crucial because the King Midas problem, the problem that King Midas faced, he specified an objective, but it was the wrong one. He shouldn't have said, "I want everything I touch to turn to gold," because that included his food and his drink and his family and so on. So you would have wanted the machine to say, "Okay, well, you say that, but I don't think that's what you really mean. Maybe what you really want is just that whenever you point to something, you want the ability to have that thing turn to gold if you choose to make it gold. So how about when you point to something and say, abracadabra, we'll turn it to gold for you. Or maybe we'll check with you first before turning it to gold," or something like that. And, you could negotiate a protocol that would have made King Midas happy and would have been quite different from his original request. And so, a machine that believes it knows the objective is going to pursue that objective. And in fact, it doesn't matter if the human is jumping up and down and saying, no, 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 don't do that. You're going to destroy the world. Because the machine, since it knows the objective and it's done the optimization, it knows that the action it's taking is correct. And whatever you're saying, whatever you're jumping up and down doing, is just noise, right? The objective is a sufficient statistic, and human behavior, subsequent human behavior, is irrelevant once you have the objective. And so by making the machine uncertain about the objective, the machine is then open. In fact, it has an incentive to acquire more information about human preferences. And the person jumping up and down and saying, no, no, you're going to destroy the world, is clearly more information about human preferences. And the machine will then defer to that request to stop doing whatever it's doing, because presumably it didn't realize that that is in fact violating some human preference that's really important. And so those two principles work together actually to make machines deferential to humans and willing to accept redirection. They have an incentive to ask permission before they do anything that might really have a negative effect because they're not sure. And machines will allow themselves to be switched off, right? Because they want to avoid doing things that will upset us. And one way to avoid doing things that upset people is to allow yourself to be switched off. So you actually have a positive incentive to allow yourself to be switched off. Whereas if you know the objective, you have no incentive to allow yourself to be switched off. In fact, you have an incentive to prevent yourself from being switched off. So those two principles, I think, are the core. And then the third principle is essentially about grounding this notion of human preferences that appears in the first two principles. And this is probably the most difficult one. But what it says is that the choices that humans make, so human behavior, provides information about human preferences. And the reason that's problematic is, of course, human beings are not rational. And their actions don't reflect their preferences in a perfect way. So, for example, if you look at Lee Sedol playing AlphaGo, right? Well, at some point, Lee Sedol makes a move which guarantees he's going to lose. Now, if you thought he was rational, you'd say, oh, well, then I guess he must want to lose. But clearly that would be a wrong conclusion to draw, right? He wants to win, but his rationality is insufficient to ensure that he always acts in that way. And so in order to understand human behavior as providing evidence for human preferences, you have to think actually about the real human cognitive architecture. In some sense, you're sort of inverting through that architecture to get at the underlying preferences. And then there are some other complications to do with the fact that our preferences may not be stable. There may be, in fact, no clear notion of what human preferences are in the first place. Mm-hmm. Our preferences are plastic, meaning that what I think I'm going to like in the future may not turn out to be what I like. I may change my preferences as a result of experience, or there's my preferences in hindsight, my preferences in anticipation, my preferences at the time. These are all different. So there's a lot of complications, but I think the complications are probably secondary. If our main goal here is to avoid the fate of the gorillas, right? Then one hopes that these considerations are secondary, and the main thing is that the machine fairly quickly learns the main things that we care about, and is also appropriately uncertain about the rest, so that it doesn't accidentally and irreversibly destroy things that we care about.
So if we can't, if you said humans' preferences are plastic, wouldn't that kind of go against what we started our conversation today with? That discussion of whether that human utility curve assignable a number is really a factor hypothesis that we started building everything upon since you were 11 years old.
It certainly is I think it requires a refinement of the theory, and in fact, I would say at the moment we just don't have a good way of thinking about it.
Mm-hmm.
And so for example, you think about taking drugs. From what I understand, it's often the case that before people take drugs, they know that they don't want to be a drug addict.
Yeah.
But the taking of drugs not only makes you a drug addict, but actually changes your whole conscious and cognitive processes so that you even start to believe that it's perfectly fine to be a drug addict.
I think it even rewires your DNA in certain ways, which make it very hard for you not only to give up, but you could have given up drugs for 20 years and then it takes only 1 or 2 hits afterwards to go right back where you were 20 years before that. And we have actually a couple of very serious drug addicts, unfortunately, in the family, and they've been trying to get clean for, in one case, maybe for 7 or 8 years. And it's been a total failure, unfortunately.
Yeah, so it's very, very difficult. And you could just say, well, okay, their preferences after taking drugs should just be discounted. But in fact, when you look at newborn babies, they don't have complex political preferences or preferences about whether man should explore the universe or remain on Earth, or they don't have preferences about free speech and any of those things. So clearly, we acquire preferences over time through experience, and you're always going to have this question: well, whose preferences are you optimizing for? The preferences you have now, or your sort of post hoc, the preferences of the future you after this sequence of experiences? And I think that's a really important question. And at the moment, from what I understand, there isn't really a good philosophical foothold which we can use to start thinking about, and then what should the programs do? So we don't know what we want to have happen as yet. But one thing that's clear is that because of plasticity, if we don't think this through carefully, you could have a situation where AI systems actually mold the preferences of humans, for example, in ways that make them easier to satisfy.
Right.
And you could say, well, this is what politicians do all the time, right? They tell people to care about certain things, about winning wars or keeping immigrants out, which are relatively easy to do, and then you deliver what you've convinced them they want.
I know you're a believer of sort of the Stephen Omohundro provable safe mathematical systems sort of line of thinking, and I had Omohundro on my show before, but there's a lot of criticism coming from a variety of people who say that the nature of intelligence is that we cannot have a provably safe, and even mathematically speaking, we cannot have a provably safe mathematical system. So there's a paper published by, I think, Stuart Armstrong from the Oxford Martin School of Future Studies. There's another paper published by Roman Yampolsky, who I interviewed a couple of weeks ago. And both of those papers put forward the claim that, or the argument, that it is impossible, in fact, to design such system, that therefore there would always be that uncertainty.
Well, so I don't think Stuart Armstrong's paper says that. I think Stuart is talking about a certain identifiability issue in the question of the combination of an irrational human with some preference function. And if you think about that combination, so if you've got an unknown human decision-making process and you have unknown preferences, and then you observe the behavior, well, you could explain the behavior in terms of many different combinations of non-rational decision-making plus preferences. So for example, Garry Kasparov you might think he's a good chess player who wants to win. But maybe he's just a really, really, really bad chess player who really, really, really wants to lose. And he's so bad that he just keeps winning all the time. Right? Now, yeah, I mean, theoretically that's possible, but to me, that would be sort of almost meaningless to ascribe to Garry Kasparov the desire to lose every single game, but just be so bad, so sort of anti-rational that he ends up winning every single game. You could also imagine actually doing, because there is a fact to the matter in some sense, right? There's a fact to the matter about what your decision-making procedure is. And you can imagine exploring it using fMRI or other kinds of neuroscience techniques. And similarly, if instead of Garry Kasparov, we were thinking about, what about AlphaGo, right? Maybe AlphaGo is a really, really bad Go player who really, really, really wants to lose and keeps on winning by accident, right? But we can go look at the software and see that that's not the case, right? So there is a fact to the matter, and it's just a question of using more sophisticated techniques, and we do science to find out the internal structure of molecules and all kinds of other stuff, based on piecing together reasonable hypotheses that explain the evidence well. And the same thing is going to be true for understanding the human cognitive process. I'm not minimizing the difficulty, but I think it's reasonable for us to proceed on the basis that we have something resembling preferences, and we have a decision-making procedure that, at least in simple cases, will tend to choose the thing that we prefer. And that's, and then the rest is sort of complications, but it's not a fundamental difficulty.
So the way I personally kind of approach this from sort of a philosophical and very poor way, perhaps, I look at it as sort of like, even from a parental point of view, when you have a child, you're giving birth to a new intelligence. And you do everything, and when they come out into the world, they're empty hard drives. They have no programming. We have to install the operating system. We have to teach them that differential thinking of uncertainty that you're talking about, your second principle, usually coming with respect to the child's parents and their elders, and so on and so on. And we can do everything we can to give them the best education, the best possible nourishing, loving environment. And so we can improve the probability that they would turn out well, but we don't have a guarantee that they would, and we don't have a guarantee that one day they would not become a Charles Manson or even Adolf Hitler, despite everything that we've done. And that's kind of my take on the nature of intelligence. Is that
so? Well, but that's because we, as I say, we don't get to design the baby, right? It's not a completely blank. We're not installing the operating system. The baby comes with actually a great deal of built-in preferences, including self-preservation, including pain avoidance, seeking pleasure, avoiding hunger, and so on. So I think by and large, babies and humans are significantly selfish entities. Whereas
selfishness is a factor of evolution and of survival in a world of scarce resources.
Right. But yeah, yes, of course it is. But we are not evolving. Our machines are not the result of evolution. We don't have to, and we shouldn't build them to be selfish. In fact, what I'm proposing in the first principle is precisely that they be perfectly altruistic towards humanity. And so if that goal is if those principles are fully realized, and obviously they need a lot more working out in practice, and they're not intended to be laws. So this is sort of a little note to the EU Parliament: please don't try to legislate Asimov's laws or Russell's laws, because these are really just intended as guidelines to AI researchers for how to think about a different kind of way of doing AI, because the the old way, I think, is much, much more problematic. And this way, I think, the core idea that uncertainty about human preferences leads to deferential behavior, I think that's a robust idea, and it will survive all of these complications and elaborations.
But Roman Yampolsky said, for example, on that note, that what if we are certain? Let's say you're saying that the robot should be uncertain in its own preferences and defer to the preferences of the human. What if the human says, "I'm certain, kill this guy. I'm certain, kill him," right? Or he says,
It doesn't matter whether he says it right. So, I mean, preferences means preferences over entire future lives, right? So I think Yampolsky needs to read what I've actually written before he proposes objections to it. So preferences means preferences over entire future lives. So it's not, that doesn't include instructions. It's not just, do I like cheese pizza or sausage pizza? It's entire future lives, including everything else that happens that I might care about. And, there's more than one person. So one person saying, kill this guy, well, the machine would say, but that guy doesn't want to be killed, so I'm not going to. Sorry. There's one aspect of human preferences which I think is problematic from the point of view of how an AI is supposed to respect human preferences, and that is preferences for the suffering of others. So if you feel better off because other people are worse off, so this is not all other things being equal. This is not, well, I want $1 more, so I'm willing to inflict a huge amount of pain on you to get $1 more. This is $0 more, right? I just want you to suffer so that I can be happy, right? That is problematic because now that creates an unnecessary trade-off between your happiness and the other person's happiness. And to me, it seems like we should not build machines to respect that form, which we might call negative altruism. And unfortunately, there is, you might think, well, negative altruists, those are like sadists, people who are just derive pleasure from cruelty. I mean, those are negative altruists. But there's a form of negative altruism which is actually much more widespread, which is economists call these positional goods, right? So it's not how much food do I have or how big is my house. It's, is my house bigger than yours, right? And so you'd actually derive happiness from the other person's house becoming smaller, even if yours remains the same size, right? And that kind of relative component of human preferences, I think it's corrosive to us, and I think it's difficult. It's going to be difficult for machines to cope with, because naturally, what the machine will want to do, for a given amount of resources, because almost all utility functions exhibit diminishing returns. So, for example, the utility of money is typically thought to be logarithmic in the amount of money that you have. So, for a given amount of resources, you can create a greater overall effect on the utility of people by giving those resources to the person who has less. But the problem with that is that it decreases the difference, and that decreasing difference, because of these positional preferences that people have, then would appear to reduce the utility of the person who has more, even though you're not actually touching that person at all, right? So this goes all the way up to the guy who wants to have the Gulfstream 6 or the Gulfstream 7 personal jet, because that makes him feel better than the person who only has the Gulfstream 4. And you give that person with a 4 a Gulfstream 5, and then the person with the 6 is less happy because he feels less of a big guy. And so that aspect of human preference structure is difficult to deal with. But besides those things, the sort of the sadism and then the I want to be bigger than you, I think it's fine. So a lot of these objections just come from not thinking through exactly what the principles are recommending.
Okay, so let's move beyond the principles and talk a little bit about the technological singularity, because Ray Kurzweil has put forward an argument that the singularity is near. And basically, we have this sort of a teleological movement from less to more intelligence in the universe, where intelligence originally originated in biology. Now it's moving in technology, and eventually, when machines become smarter than humans, somewhere around 2045, we would have the moment of the technological singularity, where all of our ability to model the future would basically fall apart. What's your take on that idea?
Well, I think there are aspects that I don't agree with, particularly trying to make predictions based on flops, so floating point operations per second. And although this is a bit facetious, you can just argue that making machines faster means you get the wrong answer more quickly. It does, making machines faster does improve the performance of certain algorithms. For example, chess playing algorithms, you can search a little bit deeper in the same amount of time. Or you can search the same amount in less time and get the same bad answer more quickly. The biggest effect I think it's had is in fact to speed up the rate of experimentation, particularly large-scale experimentation, for example, with computer vision and speech recognition. It used to take weeks and weeks and weeks to run computer vision algorithms, even on a handful of photos. But that's really, really, really changed, and I think it's accelerated the rate of research progress. But we need major breakthroughs before we have something that you might call general purpose AI. And there's no way to predict those major breakthroughs based on CPU speed. But let's assume that those breakthroughs are going to happen. And when you ask most AI researchers, although I don't put much store in the accuracy of these kinds of predictions, but when you ask people when are we likely to have general purpose or human level AI, typically you get numbers sometime around the middle of the century. And so even if Ray Kurzweil is wrong and it's nothing to do with CPU power, those breakthroughs are going to happen, and we're going to have to deal with general purpose AI. The other thing that
where do you stand on that timeline yourself among the other researchers?
I generally don't answer that question because any numerical prediction I have would be meaningless. And as I said, it requires conceptual breakthroughs to occur. But in my talks, I also point to the history of nuclear physics, where the establishment, particularly embodied in the person of Lord Rutherford, predicted with absolute confidence on September 11th, 1933, that extracting energy from atoms was impossible. It would never be done. And he was explicitly answering questions about, what do you think the prospects are for 20 or 30 years into the future? So he wasn't talking about present day technology. He was saying it was never going to be possible. And then the next morning, Leo Szilard read about this in the Times and went for a walk and invented the neutron-induced nuclear chain reaction. So, in that case, the timeline was about 16 hours. I think we need more than one breakthrough of that nature in AI, but it's very, very hard to predict when those are going to take place. So I don't usually give any numerical prediction, but to me, 2050 seems possibly a bit optimistic. So I guess I would tend towards a longer time scale. But the other point is that machines obviously already exceed human capabilities in certain narrow areas. Arithmetic, the ability to produce computer-generated imagery, right, which people can't do at all. And now chess playing and Go and video games and it's starting to look like image recognition, speech recognition, machine translation, getting up towards human level capabilities. So I would say it's the trend is towards human level or superhuman capabilities in broader and broader areas. And every time there's a conceptual breakthrough, for example, I think the biggest one that we are going to make is to extend the practical timescale of decision making. So AlphaGo looks ahead 50 moves or something into the future, which is sort of mind-boggling and superhuman. But if you're a mobile robot and your motor, the cycle time for motor control might be 10 milliseconds, well, then 50 steps into the future gets you half a second of control, right? So you can look half a second into the future. Half a second doesn't get you very far in the real world. And humans often do things on timescales of weeks or months, or they choose to do a PhD at Berkeley, and that's 5 years, or and they choose to have a career in this, and so they're making decisions are really on sort of scales of lifetimes, and a lifetime is about 20 trillion steps for the human animal.
Wow.
That's a lot, and that's in the exponent, right, or maybe even the second exponent, depending on how complex you think the problem is. So we need technologies that would allow machines to operate seamlessly across a very wide range of timescales, from milliseconds up to years, and produce coherent and effective plans of actions on those timescales. And humans do that, not always perfectly, but those are the timescales on which we function, and that would be a very, very big breakthrough. And there are pieces of that breakthrough have already occurred. I still think there are a couple of other pieces that need to be put into place before we have a full solution to that problem.
So if the pieces have occurred, we are making progress then, because unsurprisingly perhaps, but I probably did the very last interview before Dr. Marvin Minsky passed away with him. And I also did an interview with Noam Chomsky, and for different reasons, both of them denied that we have made any progress towards AGI, but all the progress they said we have made is in very narrow AI.
So I just don't think that's true at all. For example, pick probabilistic reasoning technology. We've made significant progress in probabilistic reasoning technology, and it's not narrow at all. It's completely domain independent. Search is completely domain independent, right? AlphaGo is not a Go program, right? And it proved that, or AlphaZero proved that, by also becoming the world chess champion and the world shogi champion in the space of 24 hours. It has certain clear restrictions. One is it's very short time scale. Another is it requires full observability and determinism. But it's not narrow. It's actually pretty broad.
When I gave those examples to Dr. Minsky, he said, well, the AI doesn't know that you can pull on a string, but you can't push on it.
Yeah, but so, that's another class of problem that involves different kinds of knowledge. But it seems to me that that's a relatively narrow kind of capability. That's a sort of domain-specific ability to model and simulate physical systems, and a lot of that's based on experience. So anyway, I don't think this is a good argument to get into. I think that really we have made quite a bit of progress, and I think if I say that there are maybe half a dozen major breakthroughs that we still need. Common sense knowledge and common sense reasoning is one of them, and along with that, deep understanding of natural language. Those two, I think, to some extent, go together. And but the point, coming back to the main thread of the argument, is whether there's going to be a singularity, and the point is that each of these breakthroughs creates enormous progress in the scope of things that machines can do. And within those scopes, they will far exceed human capabilities, but they will still perhaps lack other capabilities that would make them full general purpose intelligent systems. I mean, in particular, systems that would be able to sort of compete or outcompete us in the real world. So you can imagine a system that has common sense knowledge and the ability to understand natural language. It would be able to read everything the human race has ever written and integrate all of that knowledge and answer questions on that basis. It would be an unbelievably useful system for us. But it wouldn't be a general purpose AI system. It wouldn't have, for example, long range planning capabilities or motor control capabilities.
Do you think that,
and so it will be a different kind of thing from a human.
do you think
But it
that
would still be a major impact on the world.
absolutely it would have a major impact on the world? But to reach that AGI that we're talking about, do you think that consciousness is a required breakthrough that we need to accomplish, or is irrelevant?
No, I don't think it's necessary. I don't think it's irrelevant in the sense that I think, clearly I think human consciousness is real. I don't think it's illusory or, and it's the basis for, what we call value. And in particular, I think it would be a mistake for us to say, well, machines are more intelligent, so why don't we humans just disappear and let the machines have the world? And that'll be a good achievement for the human race. No, that would be a terrible mistake, because we would probably be extinguishing awareness on Earth and possibly in the universe. Mm-hmm. And there are also consequences for consciousness in terms of the rights of machines. And I think, if by some miracle we did accidentally or deliberately create conscious machines and we figured out that they were conscious, we would have some really, really complicated, difficult problems to solve, because presumably their consciousness, if it exists, is going to be totally unlike ours. It might well be that they can be conscious but have no notion of suffering. They may have no affect in that sense of suffering or happiness. And so we'd have to treat them completely differently. We'd have to have a whole new moral calculus for how to deal with the rights of machines. But this is complete speculation, because at the moment we have absolutely no theory or and the other interesting thing is that the risk, the risks of losing control have nothing to do with consciousness. And if you think about it, right? Let's suppose that by typing on my laptop, I can eventually create software that's conscious, right? Well, it's still software, right? It's still on my laptop. I can still look at all the code. I can still project what that code is going to do. And when I compute that projection, the fact that it's conscious or not conscious has absolutely nothing to do with it. Whether or not it was conscious would not change my projection of how it was going to behave at all, because I'm deriving my projection from the code of the program and how that code runs on my laptop. And so it seems quite difficult to see how consciousness is going to play any causal role in AI in the future, even if we end up with a theory of what is and isn't conscious at some point. Mm-hmm. So the achievement of AGI is going to come from solving these conceptual bottlenecks which cause current systems to fail, right? And this is the way I've always done my research and practice, is to say, okay, what is everything we know? I sort of imagine putting it all together into an AI system and sort of plunking it down in the world. Okay, well, what's the first and most obvious way that it's going to fail, right? And then I say, okay, I'll try and work on solving that problem. And that's been the way I've organized my research for the last 30 years. And we still, as I say, we still have a few more breakthroughs to go. And I think that, that even after we solve those, there may still be more. At the moment, it's a bit hard to imagine what those might be, but there probably will be some more that need to happen. But at some point, we will get there.
Professor Russell, what is the best place for people to find more about you and your work?
So I guess my webpage, in which easiest way to find my webpage is to type my name into a search engine. So that has all of my papers. It has a link to the new center that we've set up called the Center for Human Compatible AI, which is aiming, and it means what it says, right? AI that is compatible with human existence. And so that's what we're working on primarily right now, is how to make AI systems that remain under human control.
Professor Russell, we talked together, we had a conversation spanning almost 2 hours today, and I'm very grateful for that. But if you are to sort of leave us with the single most important message, perhaps, or the one thing that you would like our audience to take away from this conversation with you today, what would you like that to be?
I think just the question, what if we succeed? So if you're doing AI, just think about that question.
What if we succeed? Dr. Stuart Russell, thank you very much for being with us today.
Pleasure. Very nice talking to you.
If you guys enjoyed this show, you can help me make it better in a couple of ways. You can go and write a review on iTunes, or you can simply make a donation.